Hello and welcome. Today we're going to look at charged particles, chapter 27 of your textbook. The first thing that we need to remember is in our previous section we spoke about the magnetic force on a current. So we're going to apply this now to a electron, and remember we spoke about decay, alpha particles, beta particles. So any electrons, any beta particles, any alpha particles, anything with a charge creates a magnetic field, and therefore we can still apply our Fleming's law on that. So firstly, we're going to use to observe this force that we need to be able to see these things, these electrons or these particles, and therefore we use a electron beam tube, the one as illustrated. So in the following video they're going to show you how we use a electron beam tube to visualize the electrons and to see the force that we're talking about now.
The green line you can see across the middle of the screen is an electron beam. When we bring a magnet close to it, we can cause the beam to move in all sorts of directions. The force acting on the beam can be calculated using the equation F equals B, the magnetic field strength, multiplied by Q, the charge of one electron, multiplied by V, the velocity of each electron.
Okay, so what we saw here is we can manipulate the beam of the electron when we have magnets close to that. So that means that the electron beam creates a magnetic field, just like a current creates a magnetic field. So what we are seeing is the moment we have a magnetic field and we have an electron beam, the first thing that we need to remember is that we're using electrons and we're not using current anymore. So in the previous chapter we used Fleming's left-hand rule, okay, the one with the ring, okay. So force, that is the direction where the wire would experience a force, magnetic field and current. But as I've taught you guys before, that when they discovered the electron, they messed everything up. So we swap those two fingers. So if this is for a positive particle or for current, this is for a negative particle, electron, or a beta particle, beta negative particle. So we're going to apply Fleming's left-hand rule like this now and see how the electron deflects. So if we look here, the electron beam is going into the magnetic field. You start off, remember you swap your fingers, so you put your index finger into the green part there. Your middle finger points in the direction of the current, and then your thumb points upwards. And as this electron moves through the magnetic field, there's a constant upwards force on it, and that creates a circular motion of the electron beam. Now obviously if we have a beta particles, negative beta negative particles, the beam would look the same. If we have alpha particles, a beam of alpha particles, the beam would deflect differently. And if we have gamma rays don't have a charge, therefore they won't be affected by a magnetic field at all, so it would just go straight through. Next we're going to see how we calculate this magnetic force on a moving charge. In the previous chapter we saw that the force on a current carrying wire can be calculated by the magnetic field, the current, and the length of the wire. Okay, in this chapter we're not going to have a current anymore, but we're going to have electrons which carry a charge, either electrons or particles that have a charge, and we know that I is Q over T. So when I substitute that into my formula, I get B, okay, Q L over T. And length over time is equal to velocity because velocity is distance over time. So that ends up with a BQV. And that's the formula that they showed you there. Now, hence, if we're using an electron and the electron has a fixed charge, we can calculate this by using BeV, where B is the magnetic field, E is the charge of the electron, and V is the velocity at which the electron moves. So that force depends on the magnetic field, the charge of the object, and how fast the electrons are moving, and we call this the Bev force.
Now I've switched the direction of the beam so that it's going vertically upwards, and I've applied a uniform magnetic field across the electron tube. You'll notice that the perpendicular force acting on the electrons, according to Fleming's left-hand rule, is acting as a centripetal force, causing the electron beam to move in a circle. The radius of this circle is related to the velocity of the electrons, the charge and mass of the particles, in this case they are all electrons, and the strength of the magnetic field, or the magnetic flux density.
So since we've just seen that our Bev force also acts as a centripetal force when the magnetic field goes into a certain direction, we can now use that, and there's a crossover between the two chapters, and when we cancel out, we get that we can rearrange the equation so that we get the following, that R is equal to mv over be. Okay, so we can now calculate the radius of the practical situation. If we know the mass and the charge of the electron, we know the strength of the magnetic field, and we know the velocity. But we can also measure this in real life, and then we can use that to calculate the velocity of the electron. So that gives us a few crossover applications to this formula. From this equation, we can see that the heavier the object, the bigger the radius. The faster the objects are moving, the bigger the radius. And the stronger the magnetic field, the tighter the radius, or the smaller the radius would be. We can also rearrange that because mv is equal to momentum, so that we can say that the momentum is equal to that, and that also gives us further applications to this formula. Another interesting application to this formula is how they use this to get the mass-charge ratio of an electron. So remember, J.J. Thomson didn't know what these negative particles was, and he started doing experiments. And from this experiment, he couldn't get the mass or the charge of the electron, but he could get that ratio. And that further helped Robert Millikan later to get the charge of the electron, and once he could get the charge, he could calculate the mass as well. So here's how he used the equation to calculate the mass-charge ratio. So from our equation, we could rearrange it so that we can get the electron, charge of the electron over the mass is equal to the velocity over the magnetic field times the radius. The problem with this formula is it's very difficult to calculate the velocity of the electron beam and the radius there. So we want to try and find a way to get rid of those values. So we know that the electron beam is doing work on the electron to make it accelerate. So we know that the work done is equal to the energy transferred. Okay, and the work done is measured in electron volts, and the energy transferred is kinetic energy, half mv squared. So to get rid of the mass, we rearrange this equation and get the velocity, and we say v is equal to BeR over m, where m is the mass of the electron and v is the velocity of the electron. If we substitute it in there, we get the following, that the electron volt is equal to half the mass of the electron times BeR over the mass squared. Now that simplifies to the following. So we can basically say that EV is, if we square all of that, we're going to have the m's cancelling out, so we're going to have b squared, e squared, r squared. The m's cancel out, the 2 goes to the bottom, 2m. And then we can cancel out our e with one of those, and we end up, if we rearrange everything, that the electron charge over the mass is equal to v 2v over b squared r squared. Now we could much easier calculate the voltage that we use than the velocity. Therefore we use this application, and this is what J.J. Thomson used to calculate his charge mass over charge ratio, charge to mass ratio. So we'll continue with the rest of the chapter in the next video.